Ricky, and today I'm going to talk about engine cooling systems. Surely you know that the main purpose of a combustion in an engine is applying torque on the crankshaft, and one of the byproducts of this combustion is generated heat, and harnessing this heat energy has been a challenge for designers even at the birth of internal combustion engines, and Maybach used the first radiator that water was used in that to cool the engine of his vehicle. But all the generated energy is not going to be dumped by the cooling system. In fact, only about 30 to 35% of generated energy is taken away by this system, and about 40% is lost in friction or exists by exhaust system, and about 25 to 30% is used to produce brake power, that is the power to propel the vehicle on the road. Today, practically almost all the cars are using water-based cooling systems, but air cooling is also used on almost all the motorcycles, lawnmowers, and small light aircrafts. In this case, maybe it doesn't seem rational to use additional equipment of a separate cooling system when we can use fill-off air around the engine or fill-off oil inside the lubrication system to cool the engine and avoid drawbacks of a water-based cooling system that are corrosions, periodic maintenance, leakage, and subsequent overheating. But physics of air and oil make them inferior to water in heat dissipation. Let me start with air. Density of the air is about 830 times less than the water in the same ambient temperature, and also air has very lower heat conductivity and a specific heat capacity, so it's conceivable that to absorb a same amount of heat energy we need a very large amount of air to blow in comparison to water, and with some simple calculations we can result that an air fan with very higher power of a water pump is required to remove heat energy of the same engine. Almost the same results for using engine oil that has density of about 90% of the water, and with about 55% of the specific heat capacity, it absorbs about 50% of the heat energy in the same volume as water. And because viscosity of a typical engine oil is very higher than the water, you can understand that the oil is not a good option to be used as the main medium for cooling an engine. So we need a separate cooling system to work on the modern engines, and we cannot rely on the fill-off air around the engine or fill-off oil inside the lubrication system alone to cool the engine. In this stage, I want to have a definition, and it is definition of the coolant. Coolant is defined as the fluid that works in a cooling system as the medium to absorb the heat energy from hot surfaces and keep it or take it away to the lower temperature surroundings. Up to now, based on science and experience, best coolant has been water and water-based products. I think further explanation can help us to proceed. During a combustion engine, temperature of the flame inside the cylinder can reach up to 4000 degrees Fahrenheit, and this flame temperature can make the exhaust gas to reach up to 2000 degrees Fahrenheit, and this high temperature can turn head of the exhaust valves into red, and with more heat energy, engine parts start to melt down, and after a few minutes of operation, engine stops and parts weld into each other. But by using a coolant like water that is very cheap, has very good specific heat capacity, very good heat conductivity, density, viscosity, and flow of that inside the engine and cool that inside the radiator, engineers can keep temperature of the engine parts below boiling temperature of the water. But water has some drawbacks to be used as the coolant. First, consider the coldness of the winter that can cause water to freeze inside the cooling system on the engine, that can cause engine destruction due to restriction for coolant circulation. Also, when the water freezes, it starts to expand about 9%, and this expansion can crack the engine parts. And over time, and with more demand for less emissions and more efficient engines, temperature of them has increased, and with hotter metal surfaces, thinner oil film, and a smoother movement of engine parts on each other like piston in the cylinder has been accomplished. Also, when the coolant is in higher temperature, better heat transfer happens by blowing cool air over that. This way, reduction of coolant flow rate and using a smaller water pump is possible that is equal to more efficiency. Here, problem is that water starts to boil over in these higher temperatures. Also, water contains oxygen that is very eager to react with metal parts, and if this oxidation happens and develop, manifest corrosions that is not desirable at all. To tackle these problems, engineers have come up with some effective solutions. For the first problem, they start to use a concentration known as antifreeze in the coolants. There have been several attempts to use different materials as antifreeze. An example is salts, but salts are very corrosive and in case of leakage can cause short-circuiting on electrical systems. Also, change of their water solubility in change in temperature can cause deposits that is not good at all. Also, organic materials like sugar and honey have been tested, but other than the cost for enough concentration, their water solution can be very viscous and heterogeneous, especially in lower temperatures. And petroleum-based antifreezes have the problems of not dissolving in water and fire hazards and adverse effect on rubber host materials. After all, companies have adopted an organic compound belonging to alcohol family known as glycol or ethylene glycol. Ethylene glycol is a little toxic but dissolves very good in water and makes homogeneous solution, is not corrosive and is chemically stable in different temperatures. Also, propylene glycol, that is sister of the ethylene, with less toxicity but with higher viscosity and is more expensive and in concentration of more than 50% affects good properties of the coolant like heat transfer and freezing protection. Also, as you can see in this chart, using antifreeze in the coolant also raises the boiling temperature of that. So second drawback is also partially covered too. But increasing internal pressure of a cooling system is the main solution for low boiling temperature of the water. It is a normal physical property of the fluids, and it is a law that by increasing pressure, boiling temperature of the fluids goes up and vice versa. This is based on this law that we cannot properly cook and brew tea and coffee in higher altitudes, because higher altitude means lower pressure and water boils in lower temperature and it doesn't get hot enough to be used for brewing. According to this simple law, by increasing internal pressure of a cooling system for about 15 psi, we can increase boiling temperature of the water in that for about 45 degrees Fahrenheit. So by using both 50% of antifreeze concentration and increasing internal pressure of a cooling system, boiling temperature of the coolant in modern engines has raised to about 265 degrees Fahrenheit. But glycol cannot do anything to prevent corrosion, so using additives in the antifreeze for this purpose is inevitable. These additives that are also known as inhibitors in a conventional antifreeze are inorganic oxides like silicates and phosphates that form a protective layer over the metal parts so the coolant cannot react with them actively. These conventional antifreezes are usually green in color and need to be changed in less than every 2 years per use because these inhibitor systems are exhausted over time at the effect of heat and acidity of the coolant. But modern antifreezes that are known as extended life type use organic acid additive technology that contain inhibitors known as carboxylase, and they provide protection against corrosion by chemically interacting with metallic parts, especially aluminum parts that ever increasingly are used in modern engines. Also, in some products, mix of these two technologies known as hybrid organic acid technology used as corrosion inhibition. pH of the coolant and its degree of alkalinity that can affect aluminum parts in higher temperatures and its acidity that can contribute to corrosions on ferrous metals is very critical. So engineers in some car manufacturing companies are very scrupulous about using a specific coolant and its change and replenish intervals. After all, majority of car manufacturing companies are ordering and use antifreeze for their passenger type and light truck vehicles that in minimum meets specification and requirements of a standard ASTM D3306. Now let's study the main components, their function and working principles of a typical cooling system. The main components of a very simple cooling system that the coolant flows through them are water pump, thermostat, radiator, and the expansion and retraction valves. Of course, cooling fan, hoses, pipes, and passages in the engine block and cylinder head are part of this simple cooling system. The water pump is the heart of the system and mainly works by timing belt or chain. This ensures that every time that the engine starts, water pump starts to turn too. The water pump that is used on cars are mainly centrifugal vane impeller type, and in this type of pump, when the input shaft rotates by the pulley, the impeller that is installed on that rotates too, and its rotation sucks the coolant from inlet passage and throws outward by centrifugal force, and the charged coolant goes out of the water pump housing from the outlet passage into the engine block. Dry side of the water pump is isolated from wet side by at least one special sliding seal and bearing that use a very light flow of coolant as the lubricant. As I said, when the coolant leaves the water pump, it is forced into the engine block and flows through the water jacket surrounding cylinders and absorbs some heat energy, and then flows up into the few passages that the size of them are engineered based on coolant velocity, flow rate, and desired coolant profile. These galleries are routed to cylinder head to cool exhaust valves and passages that are hottest parts of an engine. The primary reason that the coolant first flows into the engine block and then to the cylinder head is higher temperature of the cylinder head, and to prevent thermal shock of that when cool coolant comes into the engine. Also, this arrangement helps the coolant to flow more easily based on principles of natural convection that states that the fluids tend to flow upward as their density is affected by increasing temperature, and this principle in cooling systems are known as Thermosyphon effect. At the outlet of the cylinder head, coolant meets a gate known as thermostat. As you know, thermostat is a device that can be pre-adjusted to open a passage when its temperature reaches to a certain point. Mechanical old-style thermostats use a wax pellet element inside a copper cup that interacts with a pliable diaphragm that is in contact with the piston, and the piston moves a valve that is forced into its seat by a spring, and it blocks the housing passage to the radiator. When the coolant is cold, as I said, a spring forces the valve in closed position, so coolant passage to the radiator is closed, and the coolant has to go into a bypass passage to circulate in the engine by the force of water pump, and this bypass action and coolant flowing prevents forming of hot spots when the coolant is still cold and thermostat is closed. Then by raise of engine and coolant temperature, wax starts to liquefy at a certain pre-adjusted temperature. This way it expands and pushes on the diaphragm that acts on the piston to move the valve, and at the specific temperature the valve would be in fully open position and coolant can flow almost freely to the radiator. Radiator, in simple words, is a heat exchanger that receives hot coolant from the top, guides it into tubes that have heat dissipating fins for better transfer of heat to passing air, and at the bottom there's a small tank to ensure that always there's enough coolant to be delivered to the water pump. Now, despite of the circulation, if temperature of the coolant goes over a specific temperature, an ECU that is usually ECM or PCM activates a fan or fans to boost cooling of the radiator and the coolant that is flowing inside that. Also, majority of cars have a heat exchanger that is known to be a part of air conditioning system, and this heat exchanger receives directly a portion of the coolant that comes out of the engine to heat up the interior in cold weather conditions. Even though this heat exchanger is not technically accounted as a part of the cooling system in the summer, but the fact is that it can be very effective to reduce coolant temperature in engine overheating conditions. Now I come to radiator cap. As I said, we need to build up pressure in a cooling system to increase boiling temperature of the coolant. On the other hand, as the engine works, the temperature of the coolant goes up, and when the thermostat opens at the effect of higher temperatures, the coolant flows into the whole system. Now, there are some technical issues. First, we need an accessible opening on the cooling system to fill that with the coolant and then cap it again. This opening is usually on the radiator top section, and over that there is a device known as radiator cap. Second, when the temperature of the coolant goes up, it expands and builds up pressure in the system. But the system needs a provision to release the pressure if it goes over a pre-adjusted value. This provision can be a spring type pressure valve in the radiator cap to release the pressure out of the system and prevent severe damage to the fittings and components. Now, when the engine turns off, the coolant cools down and it retracts to a smaller volume. In this case, there is another spring type pressure valve on the radiator cap that opens at the effect of negative pressure of the system and allows coolant or air to return to the radiator and prevent collapse of the components. So you can understand importance of a proper and sound radiator cap. At the output side of the radiator cap, there's an overflow tank that reserves the space intercoolers for expansion and retraction of the coolant. In some designs, engineers use a radiator without any cap and make that overflow tank pressurized by using that special cap on that. This tank, that is also known as surge tank, should be filled to a specific volume, so when the coolant expands and retracts, only air exits and returns to the system. Well, these were the main components of a very simple conventional cooling system and their working principles. But cooling system that is used on your car can vary from this in configuration and components. For example, location of the water pump and structure of the radiator can deviate from these that I have shown and presented to you. Also, on some cars that the engine and powertrain are installed in longitudinal direction, engineers use a viscous coupling that uses a liquid or wax inside that to derive the cooling fan. These couplings usually are coupled directly to the engine crankshaft on one side, and the temperature of the coolant indirectly regulates the coupling and fan speed. But the cooling systems that are used on modern cars of today can be more different and more complicated. For example, water pump can be an electric type, or thermostat can be replaced by an electric valve that is controlled by the engine ECU to regulate the passage according to the signals that two or a few coolant temperature sensors send to that ECU. Also, on some high-performance cars using turbochargers and boosted air supply systems, demand for air intercoolers to cool the charged air to increase volume efficiency and better performance of the engine under loads. Some designs use air cooling for these intercoolers, but actually more effective way is using water-based cooling systems. The point here is that the range of temperature for these intercoolers are very lower than a typical engine cooling system. So optimum way is to have a separate cooling circuit from engine cooling system for intercoolers, and usually an electric water pump circulates the coolant in that. Also, deployment of torque converters in automatic transmissions to transfer the torque raises the temperature of the automatic transmission fluid, or ATF. So they use a cooler on the transmission, or in front or in parallel position of the radiator, or even as an integrated part of that to cool the ATF. Even for high performance engines that use a lot of fuel in high load conditions and produce a lot of heat, maybe use of the cooling system alone won't remove excess heat from engine oil, and best practice would be to use a separate cooling path for the engine oil to keep temperature of that within the acceptable range. Also, designers use the heated coolant for some other applications, like heating the throttle valve for better operation in very lower temperatures, or save the energy in the coolant to heat the interior even many minutes after turning the engine off. In fact, how much we can deploy the heat energy that is reserved in the coolant, we have increased efficiency of the engine and the whole powertrain. On the other hand, just after starting the engine and when it is cold, it's very important to increase temperature of the coolant fastly to the normal operating temperature to increase fuel efficiency and controlling emissions of that engine. You can understand this importance when you know that engines wear out 4 times faster if they work in lower temperatures continually. To achieve this goal, designers can use heat energy of the exhaust gas in a special heat exchanger to heat the coolant, or block flow of cool ambient air passing over the engine using electronically controlled grill shutters that are mainly used for improving aerodynamics of the car. These advanced technologies are more significant in modern cars of today that are classified as ultra-low to conceptually zero-emission vehicles that are mainly hybrid and electric type cars. Here, question is that, is there any cooling system used on electric cars? The answer is yes. Scientifically, you cannot make a machine that is 100% efficient, and this inefficiency usually appears in the machine in the form of heat energy. This excess heat can be detrimental to the electric motor and the battery if not be taken away properly. So even electric cars have cooling systems. I talk about electric powertrains and details of these low temperature cooling systems in different videos in the future. If I want to talk more about future and advanced technologies of the cooling systems in this video, I just can say that there are 2 main fields for consideration. One of them is development of cooling system components, like use of super efficient variable speed electric water pumps that provide variable coolant flow in different temperatures to optimize cooling, and they can be boosted by an impeller that is actuated by the force of air on a moving vehicle. Or use of a special tubing for radiators that can make the turbulence in the flow of the coolant, and this way increasing rate of heat transfer and better cooling. Another field for development in the future would be thermal management technologies. When an engine is working in normal operating temperature, combustion of mixture of fuel and air and flow of hot exhaust gas and cool intake air imposes very different operating conditions for pistons, valves, engine block, cylinder head, and cylinder head gasket that is interface of engine block and cylinder head. In conventional cooling systems, there's only one water pump, one or two coolant temperature sensors, and coolant passage that always have engine block on upstream and cylinder head on downstream. Easily you can understand that these systems have major limitations in keeping temperature of different engine components within optimum operating range, but advanced thermal management technologies can take many technical issues under consideration. These issues are temperature of the cylinder walls for optimum temperature of lubricant and oil film thickness, temperature of combustion chamber for optimum fuel optimization and knock control, temperature of cylinder head to protect the exhaust valves while maintaining temperature of intake air within lower acceptable range for better volumetric efficiency, and considering characteristics of cylinder head gasket that is at the effect of different engine components and fluids, especially after engine off conditions in high temperatures and the resulted heat soak. But I think talking more about these technicalities and advanced technologies is not subject of this video. Okay, now I want to talk about some faults, symptoms, and preliminary diagnosis that you as an owner can do and save your time and money when you encounter a bad cooling system on your cars. Usually the owners find out that they have a bad cooling system on the cars when an overheating happens, and sometimes it's very late to do anything to save that engine. But it's very rare that a fault in a cooling system causes a sudden overheat and fail of the engine, and usually they start from a small defect and grow into a big problem. Here I have listed these small but significant initial defects. One of the major problems with the cooling systems is the leakage. A leakage can have many reasons, and it can start from anywhere in the system, but usually it starts with an invisible evaporation and grows into a clear reduction in level of the coolant in the system. As I said, a leakage can start from anywhere in the system, but the main reason for them is the bad sealing. So if you or a technician want to do a visual inspection to find a leaking point in the system, best practice would be checking around the connections, like around water pump housing, thermostat housing, and end of tubes and hoses. But technicians can boost the leak by pressurizing the system using special tools that are usually adopted in place of the radiator cap. Also, they can use special dyes in the system to find the leaking point using UV lights. But in practice, finding the exact leaking point can be a challenge even for an experienced technician. Sometimes a heat exchanger under the dash is losing coolant, or a leak can happen from a spot that is not visible and it flows a long distance before it gets visible. But in many cases, the owners can find the leaking point easily. If it is necessary, you can use tissue papers around connections when the engine just has turned off and is cooling, and look for any signs of coolant on them in the next morning. But remember to remove these tissues before starting the engine again. Another common issue for cooling systems is accumulation of unwanted materials on external and internal surfaces and passages. For example, dead flies and insects on the radiator fins can shut the air passage and reduce cooling capacity of the system. Or scales and mineral deposits can prevent proper heat transfer between the coolant and metal surfaces. But the biggest problem that these unwanted materials can cause is a potential clog and obstruction that they can cause because many passages in the system don't have any reserve, so coolant blockage can be catastrophic for the engine. But in many cases, you can avoid these problems if you follow the instructions that are noted in your car owner's manual or in general in maintenance section of this video. Next common problem with the cooling system is fault in active components that are thermostat, radiator cap, water pump, and cooling fan. Well, certainly these active components cannot work forever continually, and even after market parts that replace them may not function as expected, And unfortunately, in many cases, fault of them can cause major problems for the cooling system and even the engine. Even diagnosis of them may not be very easy. For example, a non-functioning thermostat can be sound, but a foreign object made it stuck open or closed. Or a cooling fan can appear faulty if the coolant temperature sensor, a relay, or wiring in the system is defective. And the last but not least initial defects returns to improper installation and services. Any bad installation and service can lead to a big problem for the cooling system. For example, air bubbles trapped in the system after adding coolant can lead to misreading of the temperature sensor or formation of hot spots because they act as insulation, and even they can reduce pump flow. Even improper installation of cylinder head gasket can cause overheating very soon. About the cylinder head gasket, you need to know that it is a kind of interface of the engine block and cylinder head, and it has many holes that are part of the passage that oil and coolant flow into them. So a defective cylinder head gasket can have different symptoms. If the gasket between the combustion chamber and the oil passage is defective, exhaust gas enters the cylinder block, and if the gasket between the combustion chamber and coolant passage be defective, you can find exhaust bubbles in the radiator and see inflated hoses when the engine is in normal operating temperature, and you will have frequent overheating and reduction in coolant amount. And if the gasket between the coolant and oil passage is bad, you can have oil in the coolant or coolant in the oil. So if you find any milky or foaming oil or coolant in the engine, it can be a sign for defective cylinder head gasket. Please note that a slight milky oil inside of the engine oil filling cap is not necessarily a sign for a bad cylinder head gasket, especially in humid or winter conditions that water condensation is more significant in engine block. Okay, now I want to talk about some technical tips and precautions for cooling systems in general. My primary advice is that you always have safety in mind and be very cautious about touching any cooling system component because they can be very hot and unreliable. For example, under some conditions, a cooling fan can come on even when the engine is off and cold. This malfunction can caused by a defective sensor, ECU, or wiring. To test the cooling fan if it is shared with the air conditioning system, you can turn on the AC system and see if the cooling fan comes on. In this case, if the cooling fan starts to work, the temperature sensor can be the culprit. Sometimes a visual inspection can be very helpful in finding root of these malfunctions and defects. So not just for the cooling system, but for all the systems that are used on your car, it's recommended that you set a schedule to visit your car based on instructions that are noted in your car owner's manual. And if a fault happens to your car, always refer to OEM service centers or reputable shop and try to follow their recommendations. For example, if they find a defective hose in the system that needs to be changed and the technician advises you to change all the other hoses used in that cooling system, you should follow that guide because these hoses are made of the same material, and a corroded one can be an indication that other hoses are in the line. In many cases, technicians recommend you to change the water pump at the same time that the timing belt or chain is replaced. Also, if the shop has installed new water pump on your car, it's normal that you have a small quantity of coolant leakage if it doesn't continue after 1 to 3 hours of new pump operation. After installing a new water pump, always flush the whole system from old coolant and fill that with fresh coolant with right antifreeze concentration, because particles in the old and contaminated coolant can damage the sliding surfaces of the new pump that can result in premature water pump defects. You need to know that professional flushing, especially for removing deposits and scales, need special equipment and procedures, and some shops can do that for you. Also remember that since the water pump is partially lubricated by the coolant, running the engine without coolant other than the danger of damage to the engine can deprive the water pump from coolant lubrication that results in pump seizure and failure. And maybe some guys advise you to remove the thermostat in the summer for better cooling. Please note that thermostat is there to make sure that the engine works in optimum temperature, and ambient temperature cannot affect this optimum temperature. Also, by removing thermostat, the coolant flows into the whole system freely, and it takes more time for the coolant to reach to that normal operating temperature. Now imagine that you are driving up hills for many minutes and engine temperature has raised at the effect of increased load and fuel consumption. Now you start to go downhill while increasing your speed. In this condition, increased flow of air air over the radiator reduces the coolant temperature dramatically, and free flow of this very lower temperature coolant into the engine can cause a thermoshock that can be detrimental for that. So you cannot find any advice in the owner's manual to remove the thermostat in the summer. In the owner's manual you can find recommendations about a coolant type and change intervals. For modern cars, many manuals recommend to use organic additive technologies that are known as extended life type coolants that are usually red in color and can stand extended warranty period of that engine. But if the owner's manual doesn't recommend for any special coolant and antifreeze, you can use conventional coolants that usually contain greenish antifreeze in them. However, there is no restriction to use more expensive extended life type coolant. An exception is old classic cars that these HOAT antifreezes may not be suitable for them. Now, if you want to switch to higher quality coolant, best practice would be to flush the whole system from the old one and fill that with new one, because mixing a higher quality coolant with lower quality one degrades the mixture to that lower quality coolant specifications. Generally, don't mix the different brands and qualities of coolant and antifreeze because they may contain different additive packages that are not compatible. Using any type of coolant and antifreeze, you need to have right antifreeze concentration according to minimum anticipated ambient temperature. Like OEM initial fill, recommended concentration is 50-50, and for lower temperatures you need to increase antifreeze concentration, but remember that going over about 70% concentration can negatively affect coolant heat dissipation and even raises the freezing point, and with less than 30% concentration the coolant cannot provide adequate protection for metal parts. Now, if you have a coolant that you don't know its antifreeze concentration, you can visit the service shop to measure that for you almost accurately using a special tool known as refractometer. Also, pH of the coolant can be a measurement for its quality. This is because engine high temperature accelerates inhibitor consumption and breakdown of glycol into acidic products that lowers pH of the coolant. So it's typically not a good practice to allow a coolant to operate in pH of lower than 7. In this case, remember that pH number is not necessarily an indication for inhibitor's concentration. And if you want to boost antifreeze concentration, never use alcohol for this purpose, because alcohol has a lower boiling point and flash point. And remember that glycol is flammable too, so never weld or use open flames near the leakages that involve antifreeze. Also, if you want to open the radiator or cooling system surge tank cap, never do that when the coolant is hot and under pressure, because as I said, coolant under pressure has higher boiling temperature, and when you open the cap, a coolant pressure drops that makes the coolant to boil over immediately. Even though radiator caps are designed to not fly off the radiator neck, but this boiling coolant can burn your hands and face. And when you want to make coolant mixture, always use right amount of water with good quality, and here good quality means clean drinkable soft water with low amount of calcium and magnesium compounds, and it's highly recommended to use the ionized or distilled water with maximum total hardness of 170 ppm. In this case, snow and rain precipitations are great only if the air quality is good and you collect them dirt-free. And at the end, remember that for your own safety, avoid contact of antifreeze with your skin and inhale of its toxic vapors, and try to keep this sweet liquid out of reach of kids and animals. I hope that this video was useful and informative for you and worth the precious time that you spent for watching that. Please subscribe to my channel if you like, and press the bell icon to be notified if I have a new video on my channel. Bye.